Let's work on question 3 over here. So compute the following improper integrals. Now, if the integral is convergent, give a value, otherwise say that it's divergent. Now, what's the intuition here in part A? When we speak about improper integrals, it means that our boundaries are not limited. So we're going until infinity. This is going to be a certain area, right? A certain area under a function. And we want to know whether that area is going to give a certain value. Is it going to approach an actual number, or is it going to approach infinity? That's what we're trying to do. Now there is a method to solve these questions, and we're going to do a bit of substitution, meaning that we're going to write this integral as the limit of a certain value, let's call that a, approaching infinity, and then we're going to substitute a with the upper boundary over here, so that we can actually solve that integral. That's why we do it. We'll have our boundaries defined from 0 to a, and over here we have 2x minus 1 dx. Now the reason we did so is because now we can actually solve this integral. We could integrate every term, and then we're going to substitute the boundaries in that solution, and then we'll see what the result is. So let's see how that works out. We will have the following. We will have, let's write over here, the limit as a approaches infinity. Now what is the integral of 2x dx? Well, that's just going to be 2x to the power of 2 divided by 2, right? That's x to the power of 1 divided by 1 plus 1. Let's also keep this one, the boundaries from 0 to a. So we write this all in brackets, yes, minus, what is the integral of 1 times dx? Well, that's just going to be x. So we close that. Now we move on. We can cancel out some stuff. 2 and 2 go away, so 2 and 2 cancel out, and we're left with the limit when a approaches infinity, and over there we have the boundaries from 0 to a, and we're left with x squared minus x. So we have x squared minus x over here. Now with that said, let's substitute the values. Let's substitute the values, the boundaries, into that expression. So we have the limit as a approaches infinity, and now we're going to do our substitution. So we plug in a into the x's. We're having x to the a into the x. We substitute a into x, so we're left with a squared minus a again, so minus a. That's the first substitution. Let's keep this all in brackets, and then we have to subtract the other thing when we substitute the other term. So 0 goes into x squared, we have 0 squared, and 0 goes into x, so minus 0. Now we close those brackets, see what we get. We have the limit when a approaches infinity, and we're left with what? We're left only with a squared minus a, because 0 squared minus 0 is just going to be 0. So we're left with a squared minus a, okay? Now, what's that going to be? What is a squared minus a? Well, a squared minus a is going to be the following. Is going to be a times a minus 1, right? A is the common factor over here. So we're left with a times a minus 1. Now, what is the intuition over here? Because we're speaking about limits, so we have to understand the intuition of a limit. The idea is that a is approaching a very large number. That's what this limit is telling us. Now, if a is approaching a very large number, what are we going to multiply? We're going to multiply a very large number, right? Think of it that way. Don't think about just infinity. It's a concept. Think of it a very, very big number times infinity minus 1. That very big number minus 1. So we actually multiply two ridiculously big numbers. So when we multiply them, it's obviously going to be a very large number as well, meaning that result will approach infinity, meaning that the area below the curve that we're working with, whatever that function looks like, is going to have an indefinite area, is not going to approach a certain value. It's not going to converge to a number, it's literally diverging. So this is a diverging integral, divergent. Hope this makes sense. In the next video we go to part B.